All right, this video is to help you understand and learn about magnets, both the mathematics and two equations, as well as using the right-hand rule to figure out which direction things are pointing. To get a little complicated, there's going to be times when you're going to be pausing this video and doing stuff for me, and then checking your answers afterward. So let's begin. Looking at your notes today, the basic idea we're going to learn behind magnets is the same as before, where fields create forces. I get to teach you about these fields and which way they point, as well as about these forces, which way those point. Now, as we know from before, when we first talked about gravitational fields, that created what we call gravitational force, which I call F of G, also called weight. Then, we also learned recently about electric fields, which I call letter E, and that created what we call electrical force, F of E, which you know as K, Q1, Q2, all over the distance between them squared. But now we're going to talk about a third kind of field. It's a magnetic field, which is to be capital B. So capital B now stands for the magnetic field. And as you can probably guess, magnetic fields create magnetic force, which are F of B. Gravity fields was meters per second squared, acceleration. Electric fields were newtons per coulomb. Magnetic fields are going to be in Teslas, like Nikola Tesla. So an example of a field would be something like 5T. That stands for 5 Tesla of field. Fields create forces. Fields create forces. Now, when it comes to natural magnets, there are only 3 elements that can become magnetic naturally. That means there are only 3 materials which can make these fields naturally. That is iron, cobalt, and nickel. In these 3 elements, something very special can occur. And that's what you're going to learn about here with domains. Now, let's say you have a really nice picture you made in 5th grade. Your parent puts it on top of the fridge with a little magnet on it, and it sticks to it. Inside that cute little magnet, probably one of those 3 materials, that magnet has a bunch of electrons in groups called domains. These can anywhere from like 1 million to hundreds of billions of electrons grouped together. In almost every material known to man, they're always all scattered out, which means they all kind of cancel out. Each one of these spins is in a different way, so they all relate to no spin. But in these 3 elements, it's possible for these arrows or domains to line up, thus forming a super strong field. So you bring that magnet home, you stick it up, and then that magnet's super strong, which means all the domains point a certain way. They can all point up, they can all point to the left or at 45 degrees, I don't care, but it's like that. This means they're going to form a super strong magnetic field around them. Now, when you start slamming the freezer door, every time you do that, one of these arrows becomes a little bit misaligned, a little bit more random. That's going to weaken the field, which is why after maybe 4 years of slamming the door, suddenly the magnet no longer holds up your photo or your art. In that case, every time you hit it, it's gone to more random nature. Now you could recharge that field by heating up that magnet, which is one of these 3 elements, and then bring another field nearby it. That would realign these domains. The most common way people see them are on credit card or hotel keys. So you go to a hotel, you give them a little card, or they give you a card, and then they program it for your room. They swipe it through a machine, and that machine is a little magnet that kind of lines up the arrows in a certain combination. Maybe like that. And it does it because room 25 has this being the only combination that'll open for that day or maybe that week. Sometimes you might actually have it in your key in your cell phone, in your pocket with your cell phone, and then next thing you know, your key no longer opens your door. It's because the cell phone, which has its own electrical field, that can move some of these around. So maybe after an hour of being with your cell phone, this thing now looks like up, up, and now down, 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 because your cell phone in this region pulled them all down. It would no longer open up your door. You have to give it back to the person in charge who makes it for you. This is the idea behind domains. And domains make fields. So looking back up here, I could say in these three elements, domains make fields, which make forces. Just like we used to say electrical fields, charges would make fields, which make forces. So the top one is for magnets. The bottom one is for charges in electrical fields. So we have a really simple rule to determine it. This one is really easy. We had negatives and positives. Fields go out from positives into negatives. Magnets are the same way, but instead of using positive and negative, they have what's called poles. So if you have a magnet, it's going to have a north pole and a south pole. You can't have an object with just a single pole. In charges, you can easily just have just a single positive charge, but you can't just have a single north. You have to have at least a north and a south. So think, north is like a positive charge, south is like a negative charge. What do two positive charges do? Attract or repel? They repel. So two north poles also repel. A north and south is like a positive and negative, those attract. And lines go out from positive, out from north, because north is like positive, and into negative. They go from north and south. So looking at this cute little thing right here, here's an example of magnet. It has two poles. Lines go out from north into south. This has got to be a north. This has got to be a south. Can you now please pause this video and then work on the next two for me and figure out what they're going to be? Pause it now. All right. And by looking at it, you could easily see for this next one, from left to right, I go south, north, north, south by the direction of the arrows. These two arrows should actually meet. There should be a dead zone in the middle. And for this one, it's going to go kind of same idea, south, north, south, north. Look at this one right here. You're about to figure out what we call the polarity of Z and Y. As in, what are they? North poles or south poles? And then I want you to rank the strength of the field for these different points, from weakest field to largest. You're about to once again pause the video and then please figure out the polarity or the north or south poles of Y and Z, as well as the smallest to largest ranking of the fields. Take some time, come up with a solution for me. Lines go out from both of these, so both of these have to be north poles. And the smallest field is when the lines are super far away, which is part A. That's a dead zone. The strongest when they're close together. That's got to be point B. It doesn't matter how close the dot is to the lines. What matters is at this point how close the lines are to each other. You can see how D's lines are closer than C's. So let's go A is the weakest, then C, then D, then B. Now at this point, we have to do something kind of special. Look where it says in and out. Here's the issue. Let's draw together an arrow pointed north on your paper. Let's say with a little N for north. That's not a pole, that's just a direction. So this arrow is pointed north on the paper. Now draw an arrow pointed south. Cool. Now let's draw an arrow pointed west. Now let's draw an arrow pointed east. So far we have 2 dimensions on here, but magnets are kind of more complex. They work in 3 dimensions. So now let me ask you, draw an arrow into the page. And at that point, things are a little bit more complicated. You can't draw an arrow into the page. It's tough. So take a look at my pen right here. If I were to put it into the page, what you'd see is that little bit right there, like an X. And indeed, that's how we draw an arrow going in. That X. That symbolizes something going into the page. Now, imagine what you'd see with this pen if I had you coming out of the page. What you see is a dot and kind of the circle around it. And that is our symbol for out. Here are the 6 major directions we talk about with magnetic fields. North on the paper, south on the paper, west, east, in and out. Do not use the phrase up or down. This right here is not up, because some people can interpret up to mean this way as well, the north direction. Up and down are not good language. They will confuse you. So let's use north, south, west, east, in and out. The reason why we're going to have to do this stuff we're about to do is because magnets are a little bit tougher. Let's say we look back at electrical fields. Here's a negative charge. Lines go in. If you put a positive charge here, that positive charge will move with the field. So it's going to be moving this way. That's its velocity. And its force will be the same way. The force and velocity go the same direction. Put a negative charge here, it will go opposite the field, and its force will go the same way. Magnets, however, don't work that way. If you put a positive charge here, it will not go with the field or against the field. It will actually go completely 90 degrees to it, and 90 degrees to it and the way it's moving. To show you, we have to use the physics idea of the right-hand rule, and here's this cute little photo right here. So if you don't mind, with both your hands, let's do the physics gang side. Step 1, both hands, make a little gun like this. Keep it, lock your fingers in place. Next off, please flick something off. Yeah, there's going to be a lot of middle fingers. This is the situation like you have in front of you. It is a 3-dimensional part. Dimension 1, dimension 2, dimension 3. Now, take some practice with me. You're going to have to manipulate your hand without moving your fingers. As an example, please, if you don't mind, with your right hand, first have your thumb pointed to the north. Right hand thumb pointed up. So like your thumb is going to follow this line. You can see how it's going that way. Then, let's have your index finger going this way. But your thumb's still going to stay going north. Take your right hand, thumb going that way, and now rotate, not your finger, but rotate your hand so that your thumb is going north and your finger's going your index finger is going to the east. If you do it right, your middle finger should be pointed into the page. We use the X for that. Again, with your right hand, thumb's going that way, field's going that way, your middle finger should be pointed in. You can't actually move this finger to left or right. It's about rotating the wrist and the elbow. That's the kind of stuff we're going to be doing. So with this, there are 3 parts of your hand: the thumb, the index, and the middle finger. Let's write them down. They each stand for a physics property. The thumb is the direction of the motion. And when it comes to magnets, there's 2 types of motion that are required. It could either be velocity or it could be current. Now, what is moving? When it comes to velocity, what's moving is the charge. So the charge Q moves with velocity V. So Q and V both tell you, oh, this has got to be the thumb. Current doesn't really have a velocity. It isn't really a charge. Current is just the letter I, which we use for current. A way to remember this is when you see your thumb, someone like going this on the highway, that stands for I need hitchhike, I need motion. That's why thumb is motion. Next up, index finger. This is going to be the direction of the field. It's the way the field points. And field, we know the letter for that is B in Tesla. So whichever way the field is, like for example, it'd be the way this arrow points would be this finger. So you line this finger up with that line. Okay, remember that? A, B, it's the second letter. It's also the second part of your hand. Second letter of your hand is B. B is field. And finally, middle finger stands for the force. The magnetic force, which is to be F sub B or just F. This is the easy one to remember. If someone goes like this to you, what does that usually mean? Yeah, it means FU. And F is force. So next time someone pisses you off, please show them the direction that the force would be, which way this thing will be pushed. And just give them a nice little flick of your middle finger. You're telling them to take a force or F off. Either one's probably acceptable. But we're not quite done yet because you can see right here, there's charge, and there's two types of charge. This is true, but where it's to be unique is that we have two hands. This is called the right hand rule because you use your right hand most of the time. You can use it anytime there's a positive charge or anytime that there's current. But if it's a left hand charge, like for example electrons, you're going to use your left hand. Right hand is for positive charges and current. Left hand to be for negative charges. Let me try two examples just so you can see what I'm talking about. This is very visual. It's because it comes from actually three-dimensional mathematics called the cross product, which some people might have had experience with, but I highly doubt it. So let's look at this example where there's numbers, we don't care about it. A wire carrying a current of 2 amps is placed in the field as shown. So you can see right here, this is the direction of the current. These are the fields. It's kind of strong because the lines are close together. We have a north pole and a south pole. Which way is the force of the wire directed? Okay. Looking over here, I have my 3 fingers. And this is current, so I'm using my right hand. Step 1. This current is going to be your thumb. So take your right hand and please make your thumb point with that current arrow, literally lined up with it. Like that. My thumb should be the same way that I is pointing. Step 2. You can see the fields going from north to south. That's what we said before. So I want my index finger to going that way. So now you're going to have to do some twisting, but your thumb's got to be with this arrow. Your index finger's to be like that arrow with your right hand. Try that out for me. Thumb. Okay, I'm going the opposite way. I'm going to flip it around. And now my thumb is heading south. My index is going to the east. My middle finger is going straight up to the sky. Except I don't like the word up. So I'm going to say it's going out of the paper. Once again, thumb to the south. Index finger's got to go in the opposite way. It's got to line up with these arrows that say B next to it. So keep my thumb south. You can see I'm going to rotate my hand. So my thumb is still going south. But now my index finger is going that way. My middle finger is going out of the page. Which is answer B. I'm telling you, there's nothing more fun than watching a bunch of students on exams trying to do these things, both in high school and college, and seeing them twist their hands in all kinds of weird ways. If you're moving your fingers like this, don't. Keep them locked, move your wrist. Let's look at the second example of doing a three of you. A horseshoe magnet is positioned. I see this is a positive y going north. That means negative y is going south. Positive x going right. That means that negative x is going left. And positive z is dot, which is out, which means that negative z is going in. Okay. What direction is the force? All right. That's looking for our middle finger. Acting on an electron. That's left hand. And it's moving in the negative x direction at point P. Let's draw that in. So that's the velocity direction. That's going to be your thumb. And I'm giving nothing else, but I see a north and south pole. Lines go from north to south. Let's draw two in and label them B. Using your left hand, not your right, your left hand, let's figure this out. Which way is the force? Okay, first off, line my thumb with that velocity arrow. Go like that. Second of all, I'm going to have to move my hand so that my index finger is pointed from north to south. You might want to stand up for this because pulling your arm back is be kind of tough. So what I'm going to do is I'm simply just going to move my hand around. My thumb is pointed to the west, which is what I want. My index finger is pointed south, and my middle finger is pointed into the page. So I know my answer has got to be into. But I don't see that here. But I know that dot is out, and that's positive z, so into has got to be negative z. At this point, you might be like, holy crap. It is complicated. Yeah, you have to keep track of a couple things, but you are more than capable of doing it. Let's just try one more before you try a couple. Looking up here, you could see something. What is the direction of the magnetic force on a proton? Okay, so that's right hand. If it's moving in the positive y direction, so it's moving this way. And I know that the field's going the other way, so I'm going to draw my field in. Which way is magnetic force? Sticking my hand, I can't make that happen. The velocity is going north, but my index has got to be going south. I literally can't make this happen. Which means there's going to be no force at all. This thing does not experience a force because you can't make your hands work out that way. So here's a cool little way of kind of making this easier for yourself. There's always pairs of directions. You can see right here. The first pair is north or south. The next possible pair is west and east. And the third possible pair is in and out. Basically, you have to be given one of each in order for it to work. Let's look at the last example. In this case, my velocity was west, so the west and east direction was taken. My field was south, so the north-south direction had to be taken. The last remaining duo that hasn't been touched yet was in and out, so the answer had to be either in or out. Just like with this one, I had one of my fingers going north or south, one going east or west, so it had to be either in or out. The force can be any way. You can have your eventually force be pointing north, west, south, or whatever. It's just a coincidence so far. Do me a favor. For these two, I'd like you to try and pause this video in a moment and a half and try to use your right hand and predict what you think it's going to be for both of them. Pause it. I'll get to you in a moment. Cool. Let's see what you came up with. Let me first use this logic to figure out what the answers could possibly be. Here is a current. Current's my right hand. And I know the wire's passing into the page. Okay, that's a B, X. So my thumb's going into the page. And I know the field is this way. Using my logic, north and south is taken. West or east is not taken, but in or out is. So it's got either west or east. So you better either get positive x or negative x. Right hand, thumb going into the paper. I got to move this south. Now, if you're really clever, you could actually make it work for you. For example, I could actually rotate the paper and make it so that I don't have to rotate my hand. So by rotating the paper, you can see now that my thumb is going into the paper and my index finger is going that way, the way that the arrows are drawn. At this point, my middle finger is pointed that way. And that way is west on the paper. West on the paper is to be negative x, which is letter C. So sometimes you could actually want to lift up your paper or rotate your paper around, and that's less work on you to make it work. The next one. I have a bunch of these x's. That means in, and there's a b next to it. So this is a super strong field. It's kind of like drawing like a really large number of lines like this, except instead of pointing north, they're pointing in. So this is a super strong magnetic field going in. There's current going to the right or east. The one direction I haven't covered so far is north or south, so I better to get north or south, top or bottom. It's either be C or E. Once again, right hand. And my thumb is going to be with the current. My field is going into the paper. When I go like this, my middle finger is now flicking off the paper because it's pointing to the north. That's to be to the top of the page. Once again, right, field to be going into the paper, rotate it, middle finger pointed to the north. So that's the major idea behind this. You're going to be doing a bunch more examples. In fact, you got a homework about it, 4 questions long, which 3 of the 4 are based on that. Let's make sure. Let's do a random example on the side now. The cool thing is you could actually theoretically pick and create examples. So let's do one. Let me pick an electron at random. And let's say we want to figure out the field. Our goal is to figure out what the field is. Let's have an electron going south. So here's the negative charge, and it's going south. And let's say it's getting pushed to the right. So the force is going to be that way. Now, something to know. This thing's going to make a circle because when it gets pushed to the right, it's a kind of curve like that. And eventually this force will also be 90 degrees. So at this point, the force will then be going more kind of that way, and eventually it's going to make a complete little circle. So this makes loops. But I'm not trying to find the circular stuff yet. I just want to find, in general, which way the field is to make this happen. So evaluate me for a second. I'm going to take my hand, thumb that way, force that way, and I have my field going in. Please take a moment and pause and figure out what is wrong with that. Again, thumb going down, middle finger to the right, index finger in. What is wrong with that? Pause, pause, pause. Did you figure it out? Electron is which hand? Left hand. Motion, force, field. So there are a couple things wrong, as you saw. It's always good to kind of reevaluate. Motion, force is that way. Field is going out of the paper. And now we have good, decent direction stuff. It's time to transition and figure out how to actually calculate forces. So I've given you 2 different ways of finding forces with your hands. One is for charges and one is for current. Same thing here. You're going to have 2 equations. One's for a moving charge, which involves velocity. The other one's on a wire with current, which is going to be current. You use 2 different hands because the charge is going to be positive or negative. But as you know, positive and negative won't affect the amount of force, it will affect the direction. So the difference between the equations is current versus velocity, whereas the difference between your hands is positive and negative. So if you want to find the force amount, that's F of B. And as we know, F of B is the force in newtons. And what finger is it? Yep, right there back at you. It's the middle finger when we talk about non-number stuff. Now, from the opening salvo today, fields make forces. So to find the amount of force, we need to know the amount of field, which is B. And B is the field in Teslas, which is, of course, the index finger on your hand. Now, for a moving charge, it has to have an actual amount of charge, which is Q, which you know is charge in coulombs, which isn't a finger, but it tells you what hand to use. Positive, you use a right hand. Negative, you use left. And then finally, if it's moving, it's got to have velocity, which is V, in meters per second. And this is, of course, your thumb. So FB equals BQV. Force equals field times charge times velocity. Wires, however, don't have charges, they don't have velocity. Wires kind of have something else. They have current, which is letter I, and the current direction is your thumb. Even my cat sneezed on that one. And finally, wires have lengths in meters. And this is no part of your hand. It's just the length of the wire. So you can see here, you have all three fingers represented. And for charges, you have a positive and negative, which represents your hand. These are the two ways to calculate the values. As for your first quick example, a 1 meter long wire has 5 amps on it. It feels 0.2 newtons of force. How strong is the field? This is a wire, so I'm going to use this relationship right here. Five amps, the length is 1. If I solve this for B by using simple mathematics, I get 0.04 Tesla. Just by dividing both sides by 5. Not too tough, right? So let's take another step. An electron going that speed, 3 times 10 to the 6, passes through at force 10 to the minus second Tesla field. Now, in order to get stuff out of this, what we're going to do is we are going to calculate the force. Since this is a charge, I'm going to use the charge equation. The field is that much. The charge of an electron is 1.6 times 10 to the minus 19. It's not negative, however, because I care about magnitude here. And the negative in front of an electron is a non-mathematical negative. It is an indication of charge, not of less than 0. And finally, the velocity is at 3 times 10 to the 6. If you multiply it out, you get 1.92 times 10 to the minus 14 newtons, which is a very tiny amount of force, but it's right. And if this was a proton instead of electron, would that change the amount? No. You still have the same number as before. What it would change, however, is the direction. Because instead of going one way, it'd be going the other. Now, I don't know which way it's going to be going, but whatever it is, be rest assured, a negative will go the opposite way. Can you please try these next two for me? Pause and wait until you or the entire class is ready. Try getting these two values using what you know. I'm waiting patiently now. And so let's try it out. Same charge as electron, that makes more sense. I have force equals QVB, or BQV, or whatever you want to call it. The force is 5 times 10 to the minus 12th. The field is B. The charge is 1.6 times 10 to the minus 19. And the velocity is 4.21 times 10 to the 7th meters per second. Solve for B. You end up getting actually 0.74 Tesla. And for the last one, this is now a two-step process. You're going to have to use F equals BIL, but you don't know the current. So first step is you're going to do Ohm's law, V equals IR. 20 volts equals the current times 400 ohms. So the current is 0.05 amps. Plug that in here. The force is 0.2. The field is unknown. The current is 0.05. The length is 1.5. And you get 2.66 Tesla is your B field, or your magnetic field. And last but not least is try one more, actually two more. Looking at this one right here, an electron has a mass of that many kilograms. It goes that far in that much field. Can you please pause and try the first one for me and find out how much force there is? I'm waiting patiently. Cool. Using the equation F equals BQV, I end up getting a number here. Now, the field is 0.6. The charge is not this number. That's a mass. It to be the same as before for an electron, times the velocity of 2.5 times 10 to the 7th. You might notice this number never gets really larger than 7 because 3 times 10 to the 8th is the speed of light, and you can't get faster than that. I get 2.4 times 10 to the minus 12 newtons. Now, if I ask you to find the acceleration, at this point people should be screaming from their seats, net force equals ma, and this is the amount of net force. You're in balance. 2.4 times 10 to the negative 12. You know the mass is 9.11 times 10 to the minus 31. And you know the acceleration is actually going to be unknown. Just solve for it. Do a little math, and you get 2.63 times 10 to the 18th meters per second squared is the acceleration. Huge acceleration is for a moment in time. Newton's second law still works here. Look at this last equation for me. Is the magnetic force on Earth, the magnetic force that Earth exerts on a compass needle more or less equal to the force that the compass needle pulls on Earth? So anytime you have a compass and just lie it flat, eventually the Earth will pull it to point north. Doing so is a force from Earth on this. How does the pull of this back on the Earth compare? Please pause, and with your last little salvo, look at your partner and kind of tell them how should the forces compare. And at this point, A on B versus B on A, Newton's third law says they're equal. The force of magnet on Earth equals the force of Earth on magnet. You have 4 homework questions to try for me. There are some people in the class who've already got them. You're going to try them, and please check with those people and make sure, because next class we have a homework quiz on the last 3 homeworks. Thank you, and I hope your day is enjoyable.